Okay, in this video, what I want to do is explore the relationship between delta G naught, which is Gibbs free energy, and what that quantity and its sign actually mean based on an example using a chemical reaction. And the chemical reaction that we're going to look at is the reaction between propane and oxygen to produce carbon dioxide and water. So I'm going to go ahead and label the propane. This is a pretty standard chemical equation that's used in college chemistry and in advanced placement courses. And so that's one of the main reasons that I'm going to pick on this equation, is because it should be something familiar that to the viewer that you may have seen before. All right, now this reaction is highly exothermic. Propane is what we call a hydrocarbon. It's a gas at room temperature, and it's readily flammable. All right, so if you've ever seen a cigarette lighter, usually it contains a mixture of propane and a close companion of propane, which is called butane, which has 4 carbons instead of 3, and so on. The point is, when you flick the lighter, a flame comes on, and so what you're witnessing in that case is the combustion of the hydrocarbon with oxygen to produce carbon dioxide gas and H2O. The reaction is highly exothermic, so the delta H for this, in this case, that I have written here, is on the order of minus 2045 kilojoules. So if you were to carry this reaction out in a calorimeter, and I'm going to draw a picture of one over here, all right, coffee cup, it's full of water, we have a thermometer, all right, and I'm going to put a box here, all right, that's going to indicate within this system, or within the calorimeter, and we're going to call the box our system, so I'm going to abbreviate it. And the water that's in the calorimeter, and the calorimeter itself, we're going to define as being the surroundings. So I'm just going to write reaction in here to mean that we consider the reaction of propane with oxygen to make the carbon dioxide and water to be our system, and the calorimeter and the water surrounding the system is the surroundings. All right, now this is a highly exothermic reaction, and what that means is that energy is going to be released from the system, okay, into the surroundings. All right, and the consequence of this is that the temperature of the surroundings is going to increase. All right, so if you were actually doing this in the laboratory with a calorimeter, you would see a temperature increase on the thermometer. So you would have a positive delta T. And remembering that delta H for using calorimetry is equal to the mass of the calorimeter times the specific heat of H2O times delta T. And in this kind of a situation where you have an exothermic reaction happening in the system, the delta H for the surroundings is going to be positive, and that's because your change in T here is also going to be positive. I mean, the main point is energy is going to move from the system into the surroundings, and when it does, kinetic energy of the surroundings is going to increase and the temperature is going to go up. All right, now if we look at the equation again, and we talk about the entropy, we see that the entropy of the system here, calculated, is 346 joule. Oh, I messed up on a unit. This is joules per Kelvin. Joules per Kelvin. All right. So when we look at the number, we see that the delta S naught of the system is a positive value. That means that when this reaction happens, the system is increasing in disorder. Now, this particular equation is one of the types that you can actually evaluate the delta S of the system by counting gas particles. So we see that for every particle of propane, there are 5 particles of oxygen added to this. So there's a total of 6 particles of gas on this side of my equation. But over here you see that 4 and 3 is 7. So there's 7 particles of gas on this side of the equation. And so in a chemical reaction that is composed of all gases, when we see an increase in the overall number of particles as we go from the reactants to the products, this means that the delta S naught is going to be a positive quantity, that disorder has increased as the reaction has proceeded. And that's confirmed when we look at the actual number for this. Now, what we want to do is relate these two numbers to the expression for delta G naught. All right, and delta G naught is equal to the sum of, or the difference, just depending on how you want to look at it, the difference of the enthalpy minus the absolute temperature times the entropy. And don't forget that the knots that I have here, this simply means that we're at the standard state, the standard thermodynamic state. So we're at 25 degrees C and we're at 1 atm external pressure. All right, so we want to explore the meaning of this relationship. Now, it's important to recognize that you can learn a lot about these quantities through observation. And what I mean by that is that when propane comes in contact with oxygen and the reaction is initiated, perhaps using a match or a flint like in a cigarette lighter, the reaction takes place without any outside intervention. And this means that the reaction that we're looking at here necessarily is a spontaneous reaction. So I'm going to write that in here. It's a spontaneous reaction because it occurs without any outside intervention. And that means that this value, the delta G naught, should be a negative quantity and it will have some kind of a magnitude. All right. Now, delta G, what does it mean exactly? You can look at this from a somewhat different angle. You can treat this as if it represents potential energy in a sense. And in chemistry, we're going to call this chemical potential. And basically what I mean by this, the fact that we can treat this value like it's a potential energy, is because based on its magnitude and its sign, this tells you whether or not essentially a reaction is going to occur because it literally is running downhill, or a reaction cannot occur because it would necessarily have to run uphill. All right, so let's go ahead and calculate this value quickly. So my delta G naught is going to be equal to, now I'm going to change the units on the enthalpy because notice that the enthalpy units are in kilojoules and the delta S naught units are in joules per Kelvin. So I'm going to change my enthalpy units into joules. And you can see here that the enthalpy of this reaction it's a huge number and it's negative. All right, meaning that the process was exothermic. All right, we're going to assume that we're at 298 Kelvin, so 25 degrees centigrade. And notice that my entropy is a positive number. And the units are joules per Kelvin. So the kelvins are going to cancel out. And since the entropy is a positive number, we see that this sign right here is going to remain as it is. So literally, this term that we have here is contributing to the overall negativeness of this number, because we have a negative big number minus a negative another negative big number because of the product between the temperature and the entropy. And the delta G that we're going to get, the delta G naught for this that we're going to get is equal to this number. So a minus 2,148,108 joules. Very negative, and its magnitude is very large. So what does this mean exactly? All right, so if I draw a picture of a hill like this, and up here is a car, which is basically our chemical reaction. All right, only the way I'm going to do this is I'm going to represent the car as being the starting reactants. So these guys are combined together, and what this delta G naught means is that this process is a downhill process. So if we nudge the car to the edge of the hill, common sense dictates that it's going to roll down without any outside intervention. And at the bottom of the hill, is going to be our reaction products. So 3 CO2s plus 4 H2Os. And this difference in here is this guy right there. All right? That's what this number means. It means that this reaction is going to happen unhindered without an outside intervention. All right? Now, one last thing. It's likely in a chemistry course that leading up to delta G naught that you are interested, or you were introduced to delta S of the universe, because delta S of the universe and delta G naught are intimately linked. You know, for a spontaneous process, the delta G naught needs to be negative with with some kind of magnitude. Delta S of the universe is literally the sum of the delta S for the system plus the delta S of the surroundings. All right? And remember that delta S of the surroundings is equal to the negative of whatever the delta H is of the system divided by absolute temperature. In this case, you see delta H of my system is a negative number, and it's large in magnitude. So that means that the delta S of your surroundings is a positive number. So when we come back to this equation, what I want to point out, and which is absolutely consistent with the delta G that we calculated, is that your delta S of your surroundings is positive in this case. And the delta S, if you remember back to the system, is also positive. So delta S for this, delta S of the universe, is also a positive number, which just shows the consistency between the two concepts.